In Module 5, we're going to study the second law of thermodynamics, and to start this, we're going to start with part 1 and try to understand what the second law means and how it can be applied to thermodynamic problems. So far in the class, in all the previous modules, we have focused on the first law. So far, we have focused on the first law. And the first law is really just conservation of energy. So energy within a system has to be conserved. And now, with our second law, we're actually going to specify a direction for all processes. So the second law, what it does is it specifies a direction for all processes. And what does that really mean? Well, it means that as humans, we can apply the first law, and we can apply the first law in any direction. There's no real sense of direction when we apply the first law, and we're going to look at some examples. But what we can say is that satisfying the first law does not mean that the actual process will take place. So what do we mean by that? So let's look at an example. Let's say we have an example with a cup of hot coffee, and let's say the coffee is at 80 degrees Celsius, and we have a room at 20 degrees. Now, if I were to ask you, you would tell me the cup of coffee left in a cooler room would eventually cool off. So you would have you would have temperature going from the coffee to the room, or heat going from the coffee to the room. So we can say that the heat loss by the coffee is equal to the heat gained by the air. And that makes sense, right? We have some heat lost to the air. The heat gains the air. The air gains some heat, and we have eventually a temperature that sort of gets to an equilibrium temperature, and this satisfies our first law. Okay, so we can say that this satisfies our first law. So we're going to say first law. Okay. Now, we know this happens. If we have coffee in a room, it's going to cool down eventually. We know that this can actually happen. But we also know from experience, we know that the reverse process will never happen. So would you ever see in a system where we have our coffee cup and air at 20 degrees? So we have air at 20 degrees, coffee at 80 degrees. Why doesn't the heat from the air go into the coffee and make the coffee even warmer? There's still heat in the air. The air is at 20 degrees Celsius, so we could technically use some heat of the air and cool down the room even more. So we could say the hot coffee could get hotter and the air colder. And this statement here also satisfies the first law. We haven't broken the first law. If we had heat coming in from the air to the coffee, we haven't broken any rules from the first law of conservation of energy. And that is why we have the second law. So the second law imposes a direction to, so the second law imposes a direction to the process. So in this case, we know from experience that if we have coffee hot and air cold, the coffee is going to get colder, the air is going to get hotter. We know the opposite is not possible. However, technically, this satisfies the first law. So it is technically possible using only the first law to prove that that is correct. Okay, and that's why we need the second law. So to conclude from this, and there are many other examples of this as well, but you can look at them in your book. So to conclude from this, we can say that processes always proceed in a certain direction and also not in the reverse direction. Okay, so from experience, we can tell that we only proceed in a certain direction with processes. Okay, the second law, what it's going to do is it's going to fix the fact that the first law can occur in both directions. Okay, the second law fixes the fact that the first law can occur in both directions. And this is going to be done with the help of a term called entropy, which we're going to be looking at a little bit later as well. Okay. The second law is also concerned, so this is just an introduction, but the second law we can say is also concerned with the quality of energy. And this quality of energy is not the same quality that we have looked at earlier. It's a different definition, okay? Essentially, the quality of the energy itself is a way to determine theoretical limits for performance on system. So this quality of energy is used to determine theoretical limits for performance on systems. Or we can just write for performance. And we're going to look at the type of systems that we're going to be studying in this class. So, in this chapter, sorry, and in this module. So, we're going to introduce the concept of a thermal energy reservoir. And this is going to be important in our analysis. So a thermal energy reservoir is a body to which or from which heat can be transferred indefinitely without changing the temperature. So, so to which or from which heat can be transferred indefinitely without changing its temperature. So an example of a reservoir is, for example, a furnace. So a furnace is a place where we burn some oil or other um, gasoline or oil or refined oil, and in this, or coal or anything else. And in this furnace, we can assume that this furnace in thermodynamics is always going to be at a constant temperature because we have a constant supply of burning materials that keeps the temperature the same. So we have a constant heat coming in from our combustion in the furnace, and the heat coming out is negligible. It essentially keeps the same heat in the system and it keeps the same temperature in our system. Another example of a reservoir is actually an interesting system. It's a two-phase system. So another example is to use a two-phase system. So what's a two-phase system? A two-phase system, if you remember, if we have our TV diagram, is a system that would be in this middle phase right here. And if the system is in the middle phase, we know that the temperature doesn't change. So for example, if we have boiling water, then that could be considered a thermal energy reservoir because the temperature of the reservoir, no matter how much heat we lose to the outside or how much heat is added, is going to keep the same temperature as long as it's boiling. Okay, in this two-phase system, it's going to be boiling. Another example of a reservoir is to think of if you're in a very, very, very big room and you're by yourself and you bring your coffee cup inside a very big room. Your coffee cup might be hotter than the room, but the amount of heat that the coffee cup exchanges with the room is so small that the room is not going to change temperature. Okay? So it can be thought of also as a very large body that is not influenced by small changes in heat. Okay, so we can think of like this could be a big room if we have a coffee cup in it, or we could also think of it as a river. If we have a river or a lake, a river or a lake is going to have a hard time changing temperature if you send very little heat into it. Okay, so those are the types of thermal energy reservoirs we're going to be looking at during this class. And there's two types of reservoirs we're going to look at. We said that there's a body to which or from which heat can be transferred. So we can take heat from the reservoir, we can transfer heat to that reservoir. And these two types of reservoirs are going to be called a source and a sink. And we use these bubbles to sort of define a source and a sink. A source is a source of heat, so it's a source where the heat is supplied to something else. So it's called, a source is a reservoir that supplies heat, and it supplies heat at a constant temperature. So it's always at the same temperature. And a sink is the opposite, it absorbs heat. Okay, so a sink actually absorbs heat. So heat is coming into a sink. Okay, so that's going to be useful in our definition of the second law and how it can be applied to systems such as heat engines or power plants. And that's what we're going to talk about now. So the system that we're going to talk about now and introduce is called a heat engine. And some of you may have heard what a heat engine is, but let's look at first a little example where we can look at an example of what could happen if we have a system inside a beaker, inside a container, and inside this container we have some fluid, and what we're going to do is we're going to insert a paddle in this fluid. So this is a little like paddle that mixes the fluid, and we're going to apply some work to the paddle. Okay, so we apply some work to the paddle, and what happens when we apply work to the paddle? Well, we can say that work, if we start paddling in the water, for example, or in the fluid, we can say that work causes our internal energy to increase, or essentially causes our temperature to increase. What happens when temperature increases? When temperature increases, we have that Q is transferred to surroundings. Okay, so if we create some heat from work, we're going to transfer it over to the surroundings. Now, if we look at the system, we can say that work can always be converted to heat. Okay, we agree. So if we put some work in, we can state that work can always be converted to heat. Okay, and that implies a direction. We go from work to heat. Now let's look at the same example and say, let's now look at the same example and reverse the process. So we still have our paddle, and now instead of having heat coming out, we're actually going to add heat. Is the heat going to create work? If we add some heat, is it going to create some work and rotate this paddle? No. We actually have no work. So what we can conclude is that heat cannot always be converted to work. So we can say that heat cannot always be converted to work. And the question is, can we convert heat into work? Well, the answer is that we need a special kind of system to convert heat to work. So we can say that converting heat to work requires a system called a heat engine. And what a heat engine does is it does the following. It receives heat from a high temperature source Once it receives the heat, it converts part of the heat to work, and then since it receives, since it converts only part of the heat to work, the rest of the heat is rejected to a sink. So we can say that it rejects waste heat to a sink. And this sink is usually a low temperature sink. So we can add that this is low temperature usually. Okay? And our final point is that it operates on a cycle. And we're going to be looking at what the cycle would be. Okay? And if we draw a diagram of what a heat engine would look like in terms of heat coming in, out, and work coming out, we can draw a simple diagram, which we're going to use a lot in this module, which has our high temperature source, which is shown at the top of our diagram. And from our high temperature source, we're going to have some Q in coming into our system, or we can also call it QH. QH stands for Q hot, okay? And this goes into our heat engine, which we're going to look at an example of a heat engine later. And from our heat engine, we get some work out, okay? Some work out of the heat engine. And we also get a rejection of heat, which we're going to call Q out or QL for Q low temperature. Okay, so QH is Q high temperature, QL is Q low temperature, and here we would have our low temperature sink. And we know that our sink and our source are going to be at a constant temperature or assumed to be at a constant temperature because it's either like a river or a system that is a two-phase system or a furnace, for example. Okay, there's many other examples, but those are some of the examples that we have. So let's look at an example of this and try to apply it to a bigger system. So the best example of a heat engine is actually a steam power plant. And a steam power plant is usually studied a lot in thermodynamics because it's the perfect thermodynamic system. It's a heat engine and we know a lot of information about it. So how does the steam power plant work? So I'm going to draw a diagram here that has 4 different parts to it. So if we take our heat engine and sort of zoom in to this part of the heat engine, we can actually draw our power plant as a replacement for that bubble that says HE or heat engine. Okay, so I'm going to draw the same boundary, but much bigger now, and we're going to draw the system within that boundary. okay? And so within that boundary, we're going to have 4 different pieces of equipment. So we're going to have a boiler at the top, and this boiler is going to be connected to a turbine, and this turbine is going to create some work, okay? And then from the turbine, we're going to go to a system called a condenser. And then from the condenser, we're going to go to a system called a pump. Which is essentially the same system as a compressor, okay, which we studied in the previous module. And that's our diagram for steam power plant. And this can be thought of as our control volume for our system. Okay, this is our control volume. And we know that the following things are happening, passing through the boundary of the control volume. So we know that the furnace, which is our high temperature sink, so usually we have a furnace in a power plant, so we can call this the furnace, is outside of our system and is supplying heat and boiling some steam. Okay, so it's boiling some water. So QH is coming across the boundary and it's boiling some water. Okay, we also know that the turbine creates some work from the fact that the steam, so steam gets boiled, it moves through, and by moving through, our steam goes through a turbine and rotates and creates some work out, and this work out is going to be useful work from our power plant, so we can create some power from this. So we see that with the heat coming in at the furnace, we're able to create some power by running it through a turbine. Okay, so turbine is a very specific system. And moving on, we then go from the turbine, we now have some high temperature gases, and now we're going to make it go through a condenser where we're going to cool down the gases and bring them back to uh, a liquid system. And here, a condenser is essentially a heat exchanger. It's the same as a heat exchanger, where we have our QL out, and our QL out is usually going to a low temperature sink, which is a river. Okay, so that's why most of power plants are in a river usually, or close to a river. And following that, once the liquid is cold again, we run it through a pump, we increase the pressure, and we bring it back to the boiler where it boils, and then it starts the process all over again. Now, one thing to note is that the work out at the turbine, so the work out that you see at the turbine, is equal to work net. And this work net is work delivered by the turbine minus the work at the pump. So we usually draw it as work net on the right side, but actually the pump is also using some work coming from the outside. So some work is coming in through the pump to run the pump, right? We need to use some work from the pump. And hopefully our work net, so our work from our turbine, is more than the work in to pump the fluid around. So we're using the boiler to boil some gas, get a very, very high pressure gas to power a turbine, and the rest of the system is to cool down all the water in the system to restart the process. So usually we have steam as our working fluid inside our heat engine. Now, in our heat engine, we can apply the first law. So we can apply the first law to the system. And that means that we can use two different ways of analyzing our terms. So we have, in our diagram, we showed that we have QL, we have QH, and we have W net. Okay, those are three terms that are crossing the boundary. We can also call these terms Q dot L, Q dot H, and work dot net. Okay, depending on what is given to us, we can use either or. So if we look at the water by itself, the steam is running through pipes. I'll draw it in blue. The steam is running through pipes that are inside our control volume. Okay, and they never leave those pipes. The only thing that leaves is energy through a heat exchanger, through a boiler, and work through our turbine and pump. But our closed system of water actually stays inside. So we can say that if we apply the first law, we can say that Q in minus work out, so first law for closed system, we can say that on the water or on the steam, Q in minus work out is equal to the change in internal energy. Okay, now if we look at the system as itself, we can also say that that means that we have the change in energy in the system, the change in internal energy in the system, since it's a cycle, and since we have nothing changing over time, we can say that the change in energy or the change in internal energy is equal to 0. Okay, so we have Q in minus work out is equal to 0. And what that means is that we can rewrite this equation by looking at what Q's are coming out and in of our system in itself. So we have QH coming in, QL coming out, and work coming out. So if we have Q in, we can say that QH is positive Q in because it's a positive Q coming in, minus QL because QL is going to be a negative, okay, since it's coming out of the system, minus our work net, which is going to be positive because it's work out. The overall work is going to be, the overall net work is going to be out. So we have this equation. And if we rearrange this equation, we can say that work net is just equal to QH minus QL. So we've now, from a very simple analysis of the first law, not looking at specific turbine or specific condenser, pump, or boiler, just looking at the system as a whole, we can say we've developed an equation that says that work net is equal to QH minus QL from the first law. And we can rewrite this equation if we want to with respect to time. So we can say power or work dot net is equal to the heat rate coming in minus the heat rate coming out. We can use both forms of the equation. So these two equations are going to be used in both forms and are going to be very useful. Okay, so let me highlight them in red here. These are going to be two equations that you're going to be using a lot. And really, you can look at them through the system, through the simplified system as well. If you look at it through the simplified system, we have our high temperature, we have our QH coming in, we have our heat engine, we have our QL coming out, and our low temperature system. And here we have a work net. If we did a first law analysis on this system right here, if we looked at what was crossing the boundary, we would get the exact same thing. We would do the sum of energy coming in minus the sum of energy coming out. So it would be, if we did the sum of, so we could say that the sum of energies in is equal to the sum of energies out. We would come out to the same exact conclusion. We would have energy in is QH, and that would be equal to the energy out, which is work net plus QL. And if we rearrange this, we get that W net is equal to QH minus QL. So two different ways of looking at it. Now, let's define a little bit more of the terms that we mean by QL, QH, and what that is. So Q dot L or QL is the energy wasted required to complete the cycle. So this QL is required because if we didn't have a QL and we didn't have a loss of temperature, our boiler would get, our system would always get hotter and hotter and hotter. QL cannot be equal to 0. Okay, so it's really important to note that QL cannot be equal to 0. Okay, because QL is the energy wasted required to complete the cycle. If we don't lose any energy through heat, then our cycle would get warmer and warmer and warmer. So we can say that Q dot L or QL cannot be equal to 0. And therefore, it means that our power net, okay, our W dot net, is always going to be less than Q dot H. If there is no heat loss, then it is impossible for us to complete the cycle over and over and over and keep the cycle the same. Okay, that's very important. And we can now determine a new term called thermal efficiency. So the thermal efficiency of our system is defined by the following equation. It's called the fraction of heat input that is converted to net work output. And this can be written as N thermal is equal to W net over Q in. Okay, or it can also be written as W dot net over Q dot in, if you use it like that. And Q dot in the case of a heat engine is just work dot net over Q dot H. Okay, so you can substitute Q in over QH. Now, this is a way to measure performance. Okay, so it measures the performance. The higher work you can get from a system with a certain amount of heat in, the better it is. So we want to get it as high as possible. We want this thermal efficiency to be as high as possible. We can substitute even further and come up with further equations for N thermal. If we look at our first law analysis, we see that work net is equal to QH minus QL. So we can say that N thermal is QH minus QL over QH. Okay, so if we don't have the work net, we can use QH and QL to figure out our thermal efficiency. And we can go even further and just simplify a little bit more. We can do 1 minus QL over QH. Okay, and a typical thermal efficiency for a power plant would be something like 30%. So, or for a heat engine in general would be something around 30%. Now, the question is, can we eliminate Q dot L? So we already addressed the problem and we said that it's impossible to eliminate Q dot L. And we explained it's because of the fact that we wouldn't be able to complete the cycle. But that's not really a satisfactory response when we're engineers. We want to try and really understand if it's possible or not to eliminate QL completely. So instead of using a power plant, which is a pretty complex system, let's use a simpler system to try and explain if we can eliminate QL or not. So we can demonstrate this with a simple heat engine, which would be a piston cylinder. So we're going to demonstrate this with a piston cylinder with two sets of stops. And we're going to see if it's possible for us to not have any QL in our system. So let's start with a system with a piston cylinder. And this piston cylinder is going to have two sets of stops, one at the bottom, one at the top. And we're going to have our piston resting on the bottom stops, and we're going to have a gas at 30 degrees Celsius. That's our starting point. Okay, and we have a certain load. So we have a load here on top of the piston. So we're trying to move a load with our system. Okay, and the next thing we're going to do is that we're going to transfer 100 kilojoules of heat from a reservoir at 100 degrees. So we have a reservoir or a source at 100 degrees, and this reservoir is going to transfer some heat in, and this amount of heat in is going to be 100 kilojoules. Okay, we're just going to come up with an example. We're going to have heat in of 100 kilojoules. Okay, now what's going to happen? The gas is going to expand. So we can say that gas expands because of the heat and raises our load to the top. Okay, so it raises our little load to the top. So in a second instance, we can take this and we can look at our system with the two stops at the bottom and the two stops at the top. And we now have a system that has our piston cylinder at the top with our load on top of it. So this is our load. And our gas temperature is now something like 90 degrees. Okay, so our gas temperature has increased to 90 degrees. Okay, it's observed to be 90 degrees. And the work on the load actually is equivalent to the increase in potential energy. So we can say that the work done in this system was 15 kilojoules. So we applied 100 kilojoules of heat and our work was equal to 15 kilojoules. So this is something that we can observe. Now, the amount of heat supplied to the gas, so Q in, was greater than the work. Where does the rest of the energy go to? The rest of the energy went to excess heat. So the 85 kilojoules went to excess heat. Okay, so we used 85 kilojoules to increase temperature. Now, is it possible to transfer 85 kilojoules of the excess heat at 90 degrees back to the reservoir at 100 degrees for later use? So now that we have a system at 90 degrees, the question is, can we put that gas at 90 degrees back into the reservoir to bring our system back? So our goal is to bring our system back to the starting position. Is it possible to transfer our 90 degrees to our source, which is at 100 degrees? No, we can't, because we can't transfer heat that is at 90 degrees Celsius to something that's already at 100 degrees Celsius. We can't go that way. So we know that heat always flows. We can state that heat always flows from high temperature to low temperature. So if our gas is at 90 degrees, our heat is not going to go back to our source at 100 degrees. So we have a problem. If we keep our reservoir under our piston cylinder device, we're not going to be able to cool our gas to restart the process, to restart the cycle. So the only way to cool the gas is to bring the system in contact with a low temperature system. So we need to move the piston cylinder device to exchange with a low temperature or low T reservoir. And then by making it exchange with a low temperature reservoir, we can now make sure that we have our system going back to 30 degrees. System can go back to 30 degrees. And once it goes back to 30 degrees, then it means that we can restart our cycle and reconnect our piston cylinder back with our original high temperature reservoir or high temperature source. Okay, so that's why in order to make a system move all the time from in order to make a system work in a cycle, you have to exchange with hot temperature and then exchange with cold temperature to bring it back down. So this is an example with a piston cylinder that might be easier to understand than the whole complex system with the 4 different devices doing it all at once in our heat engine. So what we can conclude from this is we can say that it is impossible for any device that operates on a cycle and this is important, that operates on a cycle, right? If it doesn't operate on a cycle and we're trying to do it once, we can do it once, we can heat up the system once, but we can't reuse it over and over and over. So it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. Okay, so that means that N thermal always has to be less than 1. Okay, we cannot receive heat from a single reservoir and produce a net amount of work that is equivalent to that heat. Okay, we have to produce less work because we have to use some work to cool down. We have to use some of the energy to cool down, and so we're losing some energy to cooling down the system as well. Okay, so that's our conclusion, that N thermal is equal to less than 1. And this is really the basis for our Planck statement, which is an expression of the second law. So this is called the Kelvin-Planck statement. And so this Planck statement says that no engine can have 100% efficiency. And it also says that for a power plant, the working fluid must exchange heat with the environment as well as the furnace. So we need to exchange heat with a high temperature source, but also a sink. So we can say that we need, so this is the Kelvin-Planck statement, and we can add to this Kelvin-Planck statement that we need a source and a sink for a heat engine. For a heat engine to work on a cycle. And this concludes part 1 of module 5. And we'll be back in part 2 of module 5 looking at more different devices such as refrigerators and heat pumps, and trying to analyze how refrigerators and heat pumps work. And then we'll go into studying some example problems for either heat engines such as steam power plants or refrigerator and heat pumps, which are different types of systems.